Hello everyone and welcome to this latest video as part of the RICS Tech Partner Programme. My name is Andrew Knight and I work within the thought leadership and analytics part of our organisation, looking at the effect of data, technology and innovation right across the natural and built environment. And indeed with 110,000 members working worldwide right across that property life cycle, from land through planning and development, construction, valuation, brokerage, property management, building surveying, asset management. It's a very, very broad church in terms of how data and tech and innovation is affecting our profession. And indeed, our members work right across the major asset types, whether that's land itself, commercial, residential, alternative asset types, and indeed infrastructure. So once again, a very broad canvas upon which data technology and innovation is having a profound effect. And I'm really glad to have Dalraj join me today from Concrete4Change. So welcome to the call, Dalraj. And before we get into the kind of technical side of the conversation, which is going to be fascinating, I know it'd be great to have a bit about your backstory and the origin story of Concrete4Change.
For sure. Thank you, Andrew, for having me. And it's great to be here. So, yeah, I'm one of the co-founders of Concrete4Change. We're a advanced materials startup based in Nottingham. In terms of my background, in the last few years before Concrete4Change, I've been working in kind of startup venture building, if you will, particularly with a focus on companies in the climate tech sector. I was based at the University of Warwick and I was running a startup accelerator there for a number of years. And I was essentially acting as like a advisor and a kind of assistant to a number of startups in the climate tech space, companies working on battery technologies and hydrogen focused technologies, trying to decarbonize certain supply chains, lots of very interesting things going on. And through that, kind of experience, as well as previous experiences of helping smaller businesses and having a little bit of an entrepreneurial streak, I've always been interested in how we can try to fix to the best extent possible issues to do with our climate and try to create companies and ideas and innovations and support innovations that are trying to help solve the problem. So yeah, that's my background in a very brief nutshell. And during my time at Warwick, I was lucky enough to meet my co-founders, Sid and Michael. So Dr. Sid Portfolio is the CEO and Dr. Michael Wise is the CTO of Concrete4Change, and my fellow two co-founders. So those two guys actually started the company, and I joined a couple months afterwards. But they were working at the University of Warwick out of the civil engineering lab there. So I got introduced to them whilst they were doing some initial proof of concept work with the technology itself. And yeah, it really caught my attention. I'd be lying to you if I said if I thought I'd be working in this industry 5 years ago, but here we are. But yeah, it was when they kind of explained the vision and the technology to me and kind of explained what the potential was, it just captivated me. And I thought, wow, this could really make a great difference to an industry that requires lots of innovation and needs to be pushed forward towards a more sustainable future. So yeah, I joined up as the third co-founder, if you will, looking after anything commercially focused in the company. And yeah, we've been in operations now at Concrete4Change from June of 2021. So coming up to nearly 3 years in a few months' time, which has flown by. And we've been slowly scaling up from proof of concept to now being reliably in the lab environment with our technology. And yeah, we're essentially a company that is trying to take CO2, particularly if possible CO2 that's generated from cement production, and utilize that, mineralize it, lock it away forever in concrete, to make concrete cheaper, greener, and stronger. So yeah, that's the I guess the backstory and a little bit of insight into Concrete4Change now. But yeah, happy to dig into the details.
Thanks, Dalraj. And I suppose my first question is, a fairly fundamental one, which hopefully encapsulates the problem, which is, why is the concrete industry so hard to abate? I mean, what's the fundamental issue that you're grappling with here?
It's a good question. So the fundamental problem is the production of cement. So 80% of the cost and essentially 90% of the emissions associated with concrete itself come from the production of cement. So obviously we probably know the material very well, but I guess others who maybe not don't know so much, typically cement and concrete get mixed up. But what it is essentially cement is the binder, the glue, if you will, in simple terms, within concrete. but the raw minerals required to make cement in particular, and the cement production process, particularly when you're making clinker, the raw material, one of the key ingredients within making that clinker material is the breakdown of limestone. And when you break down limestone in cement kilns, heating up in the large furnaces that they have, it naturally liberates CO2. So despite all the efforts to decarbonize, let's say, the cement furnaces and kilns, which are ongoing at the moment, it can only reduce, I'd say, 40%-ish of the emissions associated with cement production. There'll always be the inherent emissions coming from the actual processing of the raw materials and subsequent clinker production, and calcination is the right term, I should say, that happens, and then and then subsequently CO2 is emitted. So yeah, hence it's very hard to abate, as you quite rightly mentioned. But having said that, what we're trying to do is realize concrete's potential to be a CO2 sink, because it has that potential. Whilst the emissions problem is vast and it's not going away anytime soon, I think there's plenty of scope in the future, and at present, actually, with our technologies and hopefully others coming into the market to help reduce and hopefully solve the problem in the long term.
So what do you see as that potential sink for concrete with CO2? You know, is it a huge opportunity here to turn it into a sink rather than an emitter in that way?
Yes, we very much believe so. Hence the development of our technology and the mission that we're on. So I guess it's a bit of useful context. And again, I guess maybe a few of the audience may be aware of this, but again, just to lay the groundwork. So carbonation of concrete can happen naturally. So any concrete structure, a building, a bridge, a road, a pavement, any structure that's exposed to the air during its lifetime. Let's say if you had a concrete building was up for 100 years and the outer layer is exposed, that building can absorb a tiny amount of CO2 from the air during that lifetime, of the 100-year lifetime, but the amount is very minimal in the grand scheme of things. It's 0.00 multiple, lots of decimal places.
Yeah.
But what's interesting is that even with natural carbonation, the CO2 is locked away forever. And even when you demolish that structure at the end of its life, it does not leak. The only way it would leak is if you heat up that member to 800 degrees plus, which is obviously not going to happen in real life. Otherwise, we're all in trouble. So what we found, particularly Sid and Michael, when they dug into it a bit deeper, what we found is that the maximum theoretical potential to lock CO2 into concrete, to sequester CO2 into concrete, is 30% CO2 by the weight of the cement content. So cement is typically around 10 to 15% of concrete by mass. So 30% of that, 10 to 15%. Now, when we did some very rough kind of back of the hand maths, what we found is that if you were to carbonate all of the concrete that's available in the world today to that level, be able to solve the emissions problem facing the whole of the European Union and some. So all the emissions, all the CO2 that's emitted, you'd be able to lock that into all the concrete in the world, in theory. And obviously that's quite an incredible, obviously, observation. And essentially what we're trying to do is exploit that potential. Now, it's very challenging and no one's really scratched the surface of that potential, and that's what we're trying to do. And there's obviously various challenges associated with doing that reliably, cost effectively, etc., as you can imagine. But that's the potential. And in future, we have the vision that there's no reason why that each building, each concrete structure in the world cannot be a store for CO2, a reliable, safe, forever store and sink of CO2. And that's what we're trying to do.
So I guess the sort of 64 gigaton question, to use the kind of carbon analogy, is how are you at Concrete4Change trying to lock this CO2 into concrete and achieve what is, as you say, theoretically a huge opportunity here?
Yes. So again, maybe as a little bit of context before we drill in. So there are existing technologies that are looking to do this, to sequester CO2 into particularly fresh concrete when it's made initially. I guess again, members of the audience may be familiar with the likes of, for example, Carbon4Change or Solidia. Majority of technologies are coming from North America, and so we believe that we have a technology that supersedes whatever's state of the art at present. So what it involves is we are developing what we call a carrier material. So this is a porous, granular, powder-like material, very fine in size, that is specifically designed to absorb a lot of CO2. So we'll take a feedstock of CO2, let's say, for example, CO2 coming from the cement industry or from the oil and gas industry, or any particular industry, but we're focused on the cement industry where possible as a main source. And then we're looking to then inject that CO2 inside our carrier material. So we're not, one thing gets said of us, do you absorb CO2 from the air? We don't. I'm very skeptical of companies that claim that happens, but that's another topic for another day, I guess. But anyway, we inject CO2 into our carrier material. Our carrier material is designed to hold that CO2. So it's the term's called chemisorption, but so basically it's chemically bonded with our material. And then we then add our material as a additive or admixture, if you will, in concrete speak, to the concrete. So we're looking at a range of around 1% of concrete by mass, so very small addition. So that means we follow, I guess, we're trying to follow the material admixture standard as a result to positively impact the concrete. And so what happens then is that our material is designed to be uniformly, homogeneously mixed in the concrete. The CO2 then starts to slowly release and mineralize and starts to basically lock into the concrete, if you will, and starts to chemically bond within the concrete structure. So once the carrier is doing that and the CO2 starts to be absorbed by the concrete, what we're trying to effect is basically create very strong calcium carbonate based crystals in the concrete. So typically concrete goes through what's known as the hydration process, whereby primarily the calcium from cement is mixing with water to create calcium hydroxide, and subsequently the main crystal is known as portlandite in particular. And then what we're trying to do with the release of CO2 is transfer that available calcium hydroxide or portlandite into what's called calcite, essentially calcium carbonate, a very strong, stable form of calcium carbonate, which in doing so increases the strength of concrete. So it makes it a bit more dense, less porous as a result. And because of that procedure, CO2 is locked, strength will go up, and subsequently that means if you can do that, you don't necessarily need as much cement in the first instance, and you can reduce your cement content to an equivalent amount. So if, let's say, for example, we increase strength by 20% above baseline, we want to try to reduce cement by 20% to achieve the equivalent strength grade of mix. And subsequently then what we're trying to achieve is CO2 is locked away forever through mineralization. So you have the removal aspect, and then you have lesser emissions or avoided emissions through lesser cement usage, because typically it's around, let's say, for every kg of cement, typically you're looking at 0.9 kgs of CO2 emitted. Typically, it may be a little bit less now. And so with the carrier materials themselves, we're trying to develop almost like a family of these materials, so that we're trying to identify waste streams, like abundantly available waste materials around the world, whether that be, let's say, for example, woody waste material, plastic waste, waste from the glass industry, waste from the ceramics industry, abundantly available, low cost, typically landfilled. And then we're taking that as a precursor, a base, if you will. And then as a company, we're trying to develop specific formulations to transform that material into a carrier in particular. So it can take a lot of CO2 by its own weight, hold it in air. So even if you, let's say you do the loading procedure, the CO2 is in there, it won't just release it straight away. You could leave it in a container for days and it won't release any CO2. And only when it's mixed in the concrete will it start to release in the right way. There is, in our opinion, and we've done a lot of work on this, there is the wrong way to release and inject CO2, and there is a more optimal way. And we're obviously trying to do a way. You know, if, for example, if you were to release all the CO2 in the first 5 minutes, that's not great. You potentially could negatively impact the concrete, which is not what you want. So hence, our development as a company and the technology itself is all around this piece of capturing the CO2 effectively and then releasing it effectively within concrete to get the positive effects you want from carbonation. And the final point I added to this answer is, when I talk about the maximum theoretical amount of injecting CO2, typically if you were to do that, you would I'd say it's reasonable to expect the pH of concrete will go down significantly towards 9. And obviously that's not necessarily what you want, particularly for structurally reinforced applications in concrete. However, with our approach, what we're trying to do, particularly for the first generation of materials, is inject a controlled amount of CO2. So we're looking at around 1 to 5% CO2 injection by the way to cement. So we're controlling how much CO2, we're releasing it very specifically, so much so that we can keep the concrete ideally within the desired range in terms of pH, durability, workability, so that there's minimal change to the concrete as possible. If anything, it's better than what was the conventional mix, and it's enhanced as a result. So this is all part of the R&D that we're doing at the moment, and we'll continue to do going forward. So yeah, it's essentially, we're a company that's kind of on the edge of carbon capture, utilizing carbon, and cement chemistry. So it's tough. It's very fascinating as a non-chemist, non-engineer. I've learned a lot, and I'm working with some very clever people who are working on the problem. But yeah, we believe this approach can really start to unlock this potential for locking CO2. However, that being said, we need to continue to develop these materials to inject more and more CO2, and that's the plan. But we want to at least develop the first generation so we can get these into the market and test them out and showcase what they can do. And then from that base, we can start to improve them and develop next generations.
So, I mean, you touched on that fact about, you know, the controlled level of carbonation. I mean, is that a reaction to the perhaps I could say the kind of nervousness, if that's the right word, of a structural engineer when they hear the phrase carbonation, you know, carbonation of concrete? Is that trying to kind of optimize that tension potentially between the sequestration and indeed the performance of the concrete?
Very much so, and we're very conscious of that, and we want to allay those concerns. Hence the approach that we're taking in terms of minimal change to the mix design as possible, controlling and limiting the amount of CO2 that's sequestered in the early iterations of the material. And so much so, in particular, I think what's important is making sure the carbonation is uniform and homogeneous, so that it's not, let's say, agglomerated or clumped around particular critical areas of where concrete could be structurally reinforced. That's one of the key benefits of using this approach of material, because it's uniformly mixed. You're avoiding that potential scenario as well. So yeah, very much so. And so that's again, it was when we first started the company, it was one thing we identified with the existing state-of-the-art approaches was they weren't necessarily able to be applicable to precast applications, to structurally reinforced applications. And as you say, as you quite rightly point out, there are those legacy concerns, and rightly so. Above all, safety is the most important thing. We're also in alignment with that. And so when we came up with this approach, it ticked those boxes, and we believe it will at scale as well, because there's no reason why it can't work using this way and still get the benefits in particular. Having said that, we do want to start initially with the lower risk non-structural applications. I think it just makes sense to do so. Yeah. And then from that, as a base to go towards the more sophisticated structurally reinforced applications as and when we can. I think that just makes sense to do so. So yeah, we're very hot on that, and we want to, hence the development pathway we've gone down, as the feedback from the market and the value chain has very much influenced our approach.
So, I mean, it's a common question I ask when I'm sort of discussing this kind of material science area is obviously you're at lab stage now, and, you know, for any of these technologies to really have an impact, it's about scale and how they integrate with the supply chain. How do you see your technology working at that scale and within that supply chain ecosystem as well?
Yeah, so we see ourselves as a IP-driven R&D company, and so we will want to essentially be the knowledge holders, if you will, and we will have contract manufacturers who will be able to produce and deliver our carrier materials on our behalf to concrete manufacturers and cement manufacturers, and they can then implement the carrier material into the concrete. So I guess from our own company perspective, it's easier from our point of view to get to the market faster, as opposed to building our own factories and pilot plants. It is possible, but they're typically more capital intensive, and I wouldn't necessarily rule it out, but I think we want to try to get into the market as quickly as we can, and this approach is the approach we want to take in order to do that. And so as a result, what we're looking to do is take CO2 from industry, but as I said earlier, particularly from cement production. Some of the biggest cement manufacturers are starting to capture their CO2 and create purified CO2 as a result. So that'd be a prime feedstock that we could help utilize and subsequently use that CO2 to inject in our into our carrier material, using, for example, fairly sized off the tractor systems which under pressure can inject CO2 into our carrier material. And they, depending on the logistics of the customer that we're working with. So, for example, if it was a cement and concrete manufacturer like a Heidelberg, for example, we could potentially load CO2 into the carrier at the cement production site. So, put our reactor system there, do the loading procedure there, and then the loaded material can then be transported to the local concrete production sites within the given radius of, let's say, 20 kilometers or wherever it might be, not too far away. So that's, it's just easier from a logistical perspective. If, for example, it's a pure concrete manufacturer who doesn't make their own cement, typically they don't have their own source of CO2, which is not a problem. Well, unfortunately, there's not a lack of sources of CO2 in our lifetime, so they could get the CO2 again from the cement manufacturer. They could get it from the oil and gas industry. There's whatever makes more sense from a logistical cost feasibility perspective. And then again, we could do the loading procedure on the concrete production site, essentially create a silo for our carrier material just alongside the other silos for the other materials. Our reactor system could feasibly plug into their control systems as well, so that the carrier feed can go into the concrete production line as well. So in essence, we're trying to make this as easy to adopt as possible, because again, the concrete production guys don't necessarily like changing too much, and that's fine. We want to try to factor that in and make it as easy to adopt as possible. And so it's trying to make it win-win for everybody as a result. So hopefully that gives you a sense of how it would work at scale.
And I guess it's quite a big question to some extent next, but there are other materials that people are using to reduce emissions, like it's a bit of mouthful, granulated blast furnace slag and fly ash, and there's other technologies to decarbonize concrete. How would you summarize the sort of sector's view of those, how people are thinking about those alternatives and other technologies? Because obviously there's a lot of people doing hopefully very good work like yourself to look at this. How would you summarize that for our listeners?
Yeah, it's a great question, and I think it's a question that's not answered enough, and I think for the value chain at large, the construction value chain, is becoming a bit confusing, to be honest. And hopefully I can shed a bit of light and maybe clarify, or at least give my point of view anyway, and hopefully it's useful. So you're quite right. GGBS in particular and fly ash are used as the existing approaches to decarbonize traditional cement as supplementary cementitious materials. Colleagues like me saying, they struggle to say the cementitious part, but anyway, they are viable alternatives, I think. But what is the issue with those materials in particular is that of the global demand for cement, the supply of GGBS and fly ash can only satisfy 5% of the demand of cement. Primarily the means of production of steel, from which GGBS is a waste byproduct. They're changing to decarbonized methods of production, primarily electric arc furnaces. So you won't necessarily get any type of GGBS, which is kind of applicable and accepted by the regulatory bodies here within concrete. Also for fly ash, typically that's produced from coal production sites, and as you know, coal power plants are being shut down pretty much everywhere. So the availability of these materials is declining quite rapidly. There are stockpiles dotted around the place which can be reactivated, but again, that's not necessarily, it's going to run out at some point. So it's not a long-term solution, in my opinion. And from what we can see, particularly in the UK where we're based, we're currently importing our GGBS from overseas, grinding it here in the UK and claiming it's green and creating green concrete, if you will, in quotation marks. And to me, that just doesn't add up or stack up. And also when you factor in that steel production traditionally, and obviously coal power plants traditionally speaking, are also quite intensive in terms of their CO2 emissions. It's you're kicking the can down the road a little bit, but again, that's just my view. So that being said, they are useful. whilst we still have enough supply. And then when you come to the overall space of the decarbonisation of concrete, I'd break it down into 3 or 4 verticals, if you will. So the one that we're playing in, the one that we want to be the front runner in, if you will, the leader in, is the mineralization of CO2 in concrete. How do you make concrete a CO2 sink, as we've already talked about? There's lots of potential here. There's existing technologies already in play in the market, and there's vast potential here, and it makes sense from a circular point of view, taking the CO2 from cement production, trying to put it in the concrete, and do so economically and safely for value. I think it's one of the key verticals. I would say the second one is looking at how we can better utilize end-of-life concrete. So typically, and again, as you probably know, and some of the listeners know, when concrete comes to the end of its life and a structure is demolished, a lot of it, if not all of it, goes to landfill, which is a shame. You know, can we try to utilize that in fresh mixes and reduce our reliance on digging up the ground for more raw materials, and create more of a circular approach? We're really interested in that as well. We haven't really done too much work, but we think this is great. The third area is the decarbonisation of cement production. So there are companies dotted around the world, particularly again in North America, that are looking to create better, more sustainable methods of production for cement. So electrolyzed cement kilns, for example, some more cost-effective carbon capture systems. I think, again, that would go a long way to decarbonising cement production. And then finally, I'd say the last area, which is a lot more future-looking, and I don't think it will come to fruition in the medium term, is you have some companies that are looking at creating some novel, I'd say, cements, but coming from very, let's say, different materials. So let's say microorganisms or algae, or some very, let's say, out there materials which are not limestone derived, if you will. As great as that may sound on paper, as you know, the cement industry and the building industry is and it's the codes are specified on specific types of cement and concrete. So I don't necessarily see them coming to market anytime soon. But having said that, maybe in the very, very long term, there may be movements there. So broadly speaking, those what I would say are the 4 verticals in which decarbonisation is happening. And together, I think all these technologies on paper are complementary, and so the more that we push these 4 verticals, the greater the probability that we can reduce the emissions problem and achieve our targets, hopefully by the timeframes that we put out. So it's not easy, and there are I would say other factors at play here in terms of, obviously, as you know, we have regulations and regulatory standards with regards to cements and admixtures and different aspects with regards to concrete and associated materials, and rightly so. Having said that, I can only speak for our vertical in particular. There is a lot of goodwill and stakeholders that are really interested and want to push forward technology such as ours to get them to the market and get them trialed, which is great. But having said that, again, there's also the legacy concerns about, let's say, safety and making sure that things work. And I'm completely on board with that. The way I look at it, and the term that I always use, which my fellow work colleagues are probably sick of me saying, is we're trying to create this bank of evidence that our technology, again, in our case, I can only speak for our case, works. It does work at a lab scale, but it's one thing doing it at the lab scale and another thing doing it at an industrial scale, and we're completely aware of that. And with the value chain support, with working with concrete manufacturers, contractors, construction companies, surveyors, the whole value chain, we can start to pilot these different approaches and move things in the right direction at a faster pace. So the more that we can do that, the more that we can collaborate in that way, and as I say, build up this evidence bank, then it becomes irrefutable, I'd like to think, and eventually we can hopefully hit a critical point of kind of inflection of, okay, there's lots of belief now and people are much more aligned, and we can really start to accelerate. So yeah, overall, I'm optimistic that with these different verticals pulling in the right direction and development that's happening and investments happening, both in time and money towards these approaches, and the industry kind of slowly accepting it, we can make a big difference. So yeah, I am optimistic, but it is challenging, I will admit, but I think with the right conditions, we can definitely make a difference.
Simon, do you think in that endeavour and sharing your optimism that we can make significant, movement towards, net zero, particularly obviously through this issue of concrete and cement? I mean, what do you think the concrete industry will look like? Do you think it will be a mix of approaches, and do you think it will it take 5-10 years? And it's obviously very difficult to make predictions, but what would be your bet in terms of what it might look like in the next 5 or 10 years?
Yeah, the way I see it is we have to reorientate, I would say, in terms of decades instead of years. This term net zero, particularly in concrete, gets bandied about a lot, and I don't want to overuse it because it becomes a bit of an empty term. But the idea of true net zero concrete is actually concrete with no emissions. And still to this day, we haven't achieved it. That's not a bad thing. It takes time to get to these, time to achieve that from a true net zero perspective. And I think we need to factor in that the industry is relatively slow moving compared to others, and subsequently kind of reorientate our targets to say, okay, we are working as fast as we can, all the different stakeholders, and there should be actionable plans which people can see, not necessarily just rhetoric, and people are pulling in the right direction. But because as we've kind of established it, because obviously things like safety and associated topics are also of great importance, it takes time to build up this trust, and the only way you build up the trust is by proving and doing it repeatedly. And hence the work that we're doing, particularly from our R&D in our labs, we're de-risking as much as we can, if not every we can, in the lab before we go out to the pilot and industrial scale, so that we're confident it works all the time, every time. So yeah, I think people need to, if they are hopeful that it's, let's say, in 5 years, I would temper that. I would kind of tone that down a little bit. I would more reorientate towards 10, 15, 20 years in terms of real meaningful scaled emissions reduction. But I think it can come quicker, provided there's the momentum is continued to be built. So yeah, I don't think, in essence, I don't think net zero is happening anytime soon, truthfully, but that's not to say it won't happen at all. And I think in the long term, as I say, provided going in the right direction, investment keeps happening, research and development keeps happening in these different verticals, and there is kind of the right factors in place, the right conditions in place, there's no reason why it can't happen in the medium to long term, which I think is the more reasonable and realistic time frame, in my opinion.
And in that journey, and once again, it's a question I've asked of people in this kind of material science space, because there is I think sometimes a real reticence to, and I think experiment is the wrong word, but to pilot and use different approaches. Is that the key thing that our members in our profession and project sponsors and others in the supply chain need to sort of have a shift of mentality to say, let's not bet the farm, to use the phrase, let's start piloting these approaches and actually trying them, as you say, initially in low risk situations as part of a bigger project, but having that curiosity to understand what's going on in the sector, and then begin to do these small scale pilots, because as you say, this is going to be quite a long journey, but there has to be, I think, a sense of let's start piloting these to see what the real world effects are, and understand how the supply chains will have to adapt. Is that a good way of summarizing what the profession needs to do now?
Yeah, exactly. You're exactly right. And the more that can be done towards that, the better. I'd say if there could be some sort of industry kind of accepted or value chain accepted way of creating kind of these pilot opportunities on a more regular basis, almost maybe even dedicating some sites in the UK or wherever it might be towards just piloting, specifically piloting, I think that'd go a really long way to providing the platform for new technologies to come to fruition. And I think, yeah, with that kind of linkage of the value chain together, I think it makes a big difference, a massive difference. And subsequently, if surveyor groups and other groups in that area of the value chain can start almost talking about this from their perspective and working with their immediate clients, whether it be contractors and others, and construction companies, and subsequently concrete providers, I think it's great, because then you have kind of people pulling in the right direction and talking about the same topics, and more alignment can then be developed. So yeah, I'm fully in favour of that, and I think it's the best way to prove out these technologies, and at the same time, realise that actually it's R&D and things will go wrong, and this may not necessarily be great the first time, and that's fine. It's not. That's the point of the pilot, to find out the issues, try to diagnose those issues, characterise them, and try to fix them. And I think if that mindset can be adopted as well, so that there's a bit more of an iterative approach, as opposed to just this expectation that it should just work first time, which often with anything it just never really works the first time. Then I think then you can start to accelerate that and do more and more, and you can iterate quicker and faster and better, and then hopefully things can get in the right direction and accelerate. So yeah, I'm a big proponent of that, and the more we do it, the better.
Indeed, indeed. Well, it's been a fascinating conversation, and thanks ever so much for your time. And I look forward to catching up again soon, because this whole material science area is fascinating, and as you just outlined and discussed, it's a long journey, and we need to keep revisiting how we push that journey along as fast as is practical, given all the constraints that you've discussed. But for today, thanks ever so much for your time, Dalraj.
Thank you very much, Andrew, and yeah, hopefully speak to you soon.